Good evening, afternoon, morning. I guess you could be watching the replay or somewhere a good ways away from me. AP Stats CRAM crew, I am super excited. Today we are finally going to start our journey into inference. So we are finally last week we talked about sampling distributions, which y'all knew. I really like that section because it does pave the way into what we're going to start talking about today, which is inference, which is really where the rubber meets the road and where we can start using statistics for real world application. Okay, and today we're going to start today and next week we're going to be looking at inference for categorical data, in other words, proportions. And we are going to be focusing today on confidence intervals. Okay, so we are going to, that is our main focus today, is looking at confidence intervals. So I see all of you all in the chat, and I'm excited about that as well. So make sure you use the chat. Of course, you know the procedures by now. I might refer to you by your chat name. So if that's an issue, then make your chat name something that's not super specific. Check out Fiveable on all the socials, Twitter, Instagram, YouTube. I'm pretty sure they're on TikTok as well. So that is pretty fantastic. So some things coming soon. So part 2 of this stream, that we split up Unit 6 and Unit 7 into 2 parts. It's crazy to think that we're almost like getting to the end of the content with our CRAMs, but we are looking at hypothesis tests next week. Same place, slightly different time. Okay, so an hour later on the time there. The Unit 6 trivia that follows with that. So we have kind of a break here in the trivia because it is a two-part stream. So that is on April 14th, which is the following day. It's on a Wednesday at 9:30 Eastern. It'll be a great chance to look over those inference things for proportions. And, of course, our 5-hour CRAM finale, Sunday, May 16th at 1 p.m. Eastern Time. I think that's really going to be where the money's made at right there. Okay, so definitely make plans to attend that. I know all of my students, I have told them, go ahead, mark it on your calendars. It's a non-negotiable. So that is where we're at. So in this stream, since it is our first week in talking about inference, we're going to start out talking about what exactly does that word mean in terms of inference. Okay, we are going to look at what is a confidence interval then. That's the first part of inference. So what exactly is that and what is it used for? What are the parts of a confidence interval? What are the procedures used to carry that out? How do I interpret a confidence interval? There's 2 parts to that I think we'll get to today. And the example, we'll do an example at the end. All right, let me change something real quick. My background is not correct. Just now realized that. Don't know how that slipped past me. So let me fix that so it's not confusing people. Okay. That should do it. Okay, hopefully that changed on your end and you have the correct dates for the upcoming stuff. I also changed my Bitmoji to express how I feel about statistics. I like that one. There was one that had a very negative feeling. I was like, no, I don't want that. I love stats. So anyways, that is hopefully that is correct. Last week I got my time zones mixed up, so hopefully this is a lot better. So that's kind of where we're going today. Kind of finishing off with an example, and we'll look at some more examples in the 5-hour CRAM, of course. Okay, so first up, let me get my cursor back. What is inference? Real quick, someone in the chat, what do you think of when you hear the word inference? I'll give you a few minutes to answer in the chat, and let me know what does that mean to you. Barks Root Beer is the good stuff. Official sponsor of AP Statistics CRAMs. Educated guess based on some limited info. Good, I like that. Using information to make a conclusion. Also very good. Okay, Daniel says using available information to make an educated guess or approximation. All of those are really good, and I really like the fact that a lot of you included the word available. So looking at the available data and then using that to broaden our horizons to our population, which is exactly what inference is. Okay, so here's a nice little graphic that sort of explains that. So inference is, and we've talked about this procedure, you have a population of people. You take a random sample out of that population. Okay, you have a population of 10,000 and you take a random sample of 300. And as long as that sample is taken randomly, you can use, for lack of a better word, numbers about those 300 people to make an inference about the population. So take your huge population that I cannot know everything about. Okay, it's just impossible. Take a random sample so it's a good representation of that population. Do the statistics work, the numbers, okay? Oh, I thought I clicked there and I sure did. So do the numbers, and then once you do the numbers, you can use that to predict what's going on for the whole population. Okay, so that procedure of inference, taking a random sample, doing the math, quote unquote, for that smaller sample, using that math to broaden your horizons to the whole population. That is inference. So I love the looking at available data, because we typically have data available for a sample, but not for a population. So taking that available data or available information, something we have prior knowledge of, you guys just knocked it out of the park here, and broadening that spectrum to our population. That is what inference is. And of course, there's going to be two legs to that. You have your categorical data, your proportional data, and then you have your quantitative data, which we'll get into in a few weeks. And the procedures are slightly different. So what is a confidence interval then? A confidence interval is the prediction side of inference. So there's two things that we're going to be doing with inference. We're going to be using a sample to predict our population. That's where confidence interval comes in. And then we're also going to be using a sample to test against an already given claim about our population. Okay, so somebody's saying something about our population. Does our sample line up with that? So with a confidence interval, we don't know anything about the population. We're trying to find that number to stick to the population. So we take a sample and use that sample to create a prediction. Okay, so of course we're dealing with categorical data. We are going to use a sample proportion. In other words, we're going to use a p-hat. That's the phrase or the abbreviation there for sample proportion, in order to estimate our population proportion. So we always start with our sample statistic to estimate our population parameter. In this case, our sample statistic is the proportion from our sample, aka our p-hat. We're going to use that sample data to see what's going on with our population data. And this kind of gives you a visual for what a confidence interval is. So we take our sample, and let's say we're asking our sample, how many of you are allergic to shellfish? Okay, some people have allergies associated with shellfish. So how many people are allergic to shellfish? We can't know that about every single person in the world, but we can know it about a random sample of maybe a few hundred people. So out of those few hundred people, how many people are allergic to shellfish? Actually, my dad and my mother-in-law both are allergic to shellfish. So that would, and you would get a certain proportion. Let's say that 8% of our sample is allergic to shellfish. So to create our confidence interval, 8% would be in the middle. So our sample effect size, that's what this publication is used. Our sample proportion is in the middle. It is our, I'm sorry, Ryan, yeah. It is, I imagine it is a struggle. I know I feel bad for my dad anytime we go to the beach, and we have to be careful what we order, not to order anything that's going to, send him into anaphylactic shock or anything. So, so let's say 8%. Okay, 8% is in the middle, and from that number in the middle, we're going to add a little bit and subtract a little bit, and that creates our interval, our confidence interval, that gives us the range that we're pretty certain the population proportion of adults allergic to shellfish would fall between. Okay, so we're basically taking our sample proportion and creating a buffer zone around that. What is the statistical term used for that buffer zone? Can anybody remind us of that term? Yes, so Jay says confidence interval. The confidence interval is the entire interval from the beginning to the end. What I was looking for was margin of error, which is just that amount, that buffer zone that we add and subtract from our population, or from our sample proportion. Too many P words. That amount that we add or subtract from our sample proportion, that is your margin of error, and that gives you 2 endpoints, which creates your confidence interval. Okay, but that margin of error is important to know. So one thing to know about confidence intervals is they're based on, as you can see, going back to that graphic, this was a 95% confidence interval. Okay, so that basically means that we're pretty certain that the confidence interval, we're 95% confident that our population proportion is somewhere in this interval. So that leaves you with 2.5% on each side that it could fall out of. Okay? So confidence level, let me see here real quick, guys. I really want it to be not popping all up at the same time. Apparently messed that up. I'm going to fix that. Well, it is not wanting to cooperate with me here. Oh, there we go. Let's go by paragraph. And let's see. I don't know if this is... I'm not going to go through and do all that for all of them. Okay, so the confidence level is the percentage of samples that is going to generate a confidence interval that would contain the true proportion. That is a mouthful. I really want to unpack that. So, in other words, a 95% confidence interval, like we were just looking at, means that if we were to repeat that sampling process many times, in other words, if we were to create 1,000 samples, okay, take 1,000 random samples from the same population, 95% of those, if I did 1,000, that would be 950 of those samples would generate confidence intervals that would contain the true population proportion, okay? And there's some really cool applets that maybe we can come back to maybe next week once we know a little bit more about confidence intervals and we can go through some of the basic stuff. Or actually 2 weeks from now we're doing means. And I can show you kind of what that means. So if I were to take 1,000 samples from the same population, if I were to create 95% confidence intervals off of each sample, that would mean that 950 of those 1,000 confidence intervals would contain that true population proportion, the proportion of all U.S. adults who are allergic to shellfish or whatever the problem might be talking about, which is a pretty good likelihood, okay? So that means you can be 95% confident that you have found an interval that contains the true population proportion. So some things to know. As your confidence level goes up, so if I increase from 95 to 99%, my interval is going to widen. So maybe 95% is right here on my graph. 99% is going to widen out a little bit. Okay, going back to that normal curve we saw a minute ago, you have 2.5% on each tail. The curve doesn't change, it's just you're widening it out so that the tails are smaller. Okay, so as the confidence level goes up, the interval is also going to go up. Okay, so that's an important relationship to know. What happens to the interval as the confidence level goes up? And then the other connection here is what happens to the interval as our sample size goes up. So if I increase my sample size, our interval is going to become smaller. Okay, that's changing the whole normal curve there, because as the sample size goes up, that is going to affect our standard deviation. Okay, so going back to that curve, just to use this as an example. If I take this data and I make it into I keep everything the same except for the 99%, 95 I change to 99. My curve is the exact same. I'm just going to go 2% further to the left and 2% further to the right. Therefore, my interval widens. Okay. Now, if I change my sample size, then the whole curve changes. The scale on my x-axis changes, because by changing the sample size, I am now changing the standard deviation. Remember, we talked about it last week with sampling distributions, okay, which is exactly what we're looking at here. As I take a larger sample, remember how it squeezed that curve in, okay? It changes the whole layout of the normal curve. Changing the confidence level doesn't change anything. It just shifts the endpoints, okay? But that sample size is going to make the interval become smaller. So looking back at the chat, I kind of got distracted there by the slides. The margin of error is not the same thing as the standard error, and we will talk about that in just a second. The standard error is one of the two parts that make up the margin of error, and that's an important distinction to make. Are there slides available for this? I'm not sure what it looks like on the student end. So there normally is, I think, through maybe Airtable. So I'm not sure if maybe Sander, you want to look into that. They should be up after the replay either way, but I'm not sure why they're maybe not showing up right now. Okay. All right, so here is our confidence interval. This is the formula for our confidence interval if we have one proportion. So you have your point estimate, that is your sample statistic. You have a proportion for your sample, so your p-hat, okay? And then you add and subtract the margin of error, okay? And then your margin of error has two parts. It has a Z star. There should be a star here. I just couldn't get it to type in right. They kept doing a multiplication sign. And then you have your standard error. So this comes back to that question that we had in the chat a minute ago. So the margin of error is everything after the plus minus sign. The standard error, which is on your formula sheet, is the standard deviation formula that you're kind of familiar with. Okay, we used this last week with sampling distributions. So whenever I combine those two, my critical value, which for proportions is a z-score. Proportions is always z-score. That's one thing to definitely know. and I take that z-score, multiply it times my standard deviation. Those two things together will create my margin of error. That's everything that I'm adding and subtracting to my population or my sample proportion to create my confidence interval. Okay, so this is my buffer zone. Everything after the plus minus is my buffer zone or my margin of error, made up of two parts: my critical value, which is based off of a normal curve, and then my standard error, which is the standard deviation formula. It's on your reference page. Okay, so these are the ways that I think it is best to break down doing a confidence interval. And we're going to use the same steps for a hypothesis test next week. Okay, so start out by stating what the problem is and what parameter it is that you're trying to estimate. Second, you want to plan, which are going to be some conditions you have to check. You're going to go back and do that formula we just talked about, probably through your calculator, which I will walk you through today. I have that set up for us to go. And then lastly, you're going to conclude. What does that answer mean? You know, in stats, context is important. No numbers with no context to it. So those are the kind of 4 steps. So I always use SPDC. Anytime with any type of inference, because you can use this also with hypothesis tests, which we will, is SPDC. State, plan, do, conclude. Okay, you can come up with a nice fun acronym for that. I've heard several of them. Just goofy stuff. Okay, the one I've always went with, just because it's like the most goofy, weird thing ever, is soggy pudding does coagulate. Don't know where that came from in my mind. My mind works in a weird way. But that was the first like weird, you know, like in trig, you have some old hippie called another hippie tripping on acid for SOHCAHTOA. And it gives you a chance to, you know, I guess talk about hippies in math class. So I was thinking, what can I put together for SPDC? And that was what my brain did. So I've just remembered it since then. But SPDC, some teachers use panic or phantom. I like SPDC for all inference. It just keeps things consistent. There's some key buzzwords you see, and as you see those, you just know I got to do a SPDC problem. Okay? All right, so stating the parameter. I really wish it were not all coming in at once, but oh well. I'll be sure that's correct for next week. So start off by stating the parameter that you are trying to estimate using your confidence interval. If you were trying to estimate the true proportion of U.S. adults who are who like baseball. Okay, I'm going to go away from the shellfish example because it brings up some bad times for a lot of people maybe. Okay, so the true proportion of U.S. adults who like baseball. Well, you can ask a few hundred people, do you like baseball, yes or no? And they could answer, and then you could use that to estimate what the true proportion is for all U.S. adults. And that is what a confidence interval is aimed at doing. So if you're looking to estimate that true p-value, notice there's not a hat here, then you need to tell me what that is. Okay, p equals, what are we trying to estimate? What's the problem about? This is where that context comes into play. And including the word true is telling the reader that you're trying to estimate the population proportion. We're not estimating our sample proportion. We have good, hard data for what that is. There's my captions back. Sorry about that. So by stating that in the beginning, if we start off and do our state the parameters in the very, very beginning, then that is going to tell the reader what our context is, and it covers that context piece right out of the gate. Okay? So state the parameter, what it is you're trying to estimate. Okay? So the next thing, you have to plan the problem. Okay? So going back to our formula, I really like what Sandra just put in the chat. Some sources might use pi. A lot of them will also use rho, which is the Greek letter P, sort of. And I think that's good, because a lot of times you are talking about a lot of P's. So having something other than P, you have your P hat, you have your P value when we get to hypothesis test. So having one less P sometimes is good, instead of, so you could use pi or rho, which looks like a P, so it's kind of hard to tell. All right, so once we've stated that, all right, the next step, regardless of what acronym you're using, so if you're doing SPDC, so state, then you want to plan, okay, which means there are some conditions you have to check. So think back to geometry class, or last week when we talked about sampling distributions. So in geometry class, you have to do proofs. Anytime you state something, you have to tell where did that come from, okay? And that's sort of what we're doing here. Like, how do I know that this formula is good for the situation that we're in? What in my problem, in my situation, tells us that this formula is going to work? So I'm going to give you guys a minute to answer. What are the 3 conditions for inference, especially a confidence interval here? Yes, 4 quadrants paper is great, Sandra. I'm glad you added that in there. Okay, we got 1, normalcy. Got to make sure that our sampling distribution is normal. What are the other 2 conditions? All right, large counts is going to match with that normal. So those 2 are really 1 condition. Random and independent, that is correct. Okay, so those are the 3 things that we need to check so that we know that this formula here works. Okay, and that really follows through all the way through the rest of Unit 6, all the way through Unit 7, sort of into Unit 8, a little change there for normal, because chi-squared is not a normal curve, but it definitely just kind of keeps following on through. All right, so the first condition is random, and if we're doing a 2 proportion interval, so if we are comparing the difference in 2 proportions, maybe the group of teens and adults who like baseball, and seeing if there's any difference, then you have to make sure that both samples are random. I can't take a biased sample of teenagers and a random sample of adults. It wouldn't really work. Okay, so the reason why that's important, and I think this is important to notice, is that by having a random sample, our sample proportion is a good estimation of our population. Okay, so for this formula to work, my middle of my interval has to match my population. So therefore it has to be a random sample. So by the sample being random, that tells us that our p-hat is an unbiased, good estimator. It's a good place to start for our confidence interval. So that's why that condition is important. All 3 parts of our formula matches with one of these conditions. The next one is independence. Okay, and I just sort of always have went by a can statement and said the population is reasonable to believe there is at least, if we took a sample of 1,000, there's at least 10,000 U.S. adults. Okay, that's true. We know that's true. So if that were the case, then the independence condition is met. And the independence condition is important because it allows us to use our standard error or standard deviation formula. Okay, so random goes with our point estimate, independence goes with our standard error, and then normal, which is the large counts condition for proportions, tells us that the z-score is a good critical value. Our sampling distribution is approximately normal. Okay, we looked at that last week. As we increased our sample size, it made our curve more and more normal. And so we need to make sure there's at least 10 expected successes and failures. So n times p is at least 10, and n 1 minus p, that's the complement there is at least 10. So if there are 2 samples, make sure you use the P combined that is on your formula sheet to be sure of normality. Okay, so it's a little bit different there if you have 2 samples, which we're going to look at with, I think, next week's example, which very much so matches what we're doing this week, is going to be a 2 sample test. Okay. So yeah, so all 3 conditions match to the 3 parts of the formula. When I came to that realization, it all of a sudden made sense. Why am I checking these conditions? So that I can use that formula that's we've been using all along. Okay. So I think this slide here is a great slide to really focus on. It gives you the conditions, it gives you the formula, and it makes that connection. You're not just checking conditions because your stats teacher told you to do so, which that is true as well, but you're doing it to verify that the formula we are always going to is actually valid for our situation, just like a proof in geometry class. Yeah, sure, we know side angle side, but how does that match with this particular context? All right, so the next step, so state and to plan, the next step is to do. So we have to do the math. We got to do the formula. Finally, we're getting to some math here, right? We're not just writing out paragraphs. Okay, and that's where your formula comes into play. Or you can use your handy dandy, what do y'all think? What can we use? Your abacus, right? Your handy dandy abacus. Some of y'all probably don't even know what an abacus is. Calculator, you know, same difference, right? There's not a calculator emoji. That drove me crazy when I was creating this, but an abacus came up and I said, hey, what the heck? I'm pretty sure an abacus will not do a 1 prop Z interval, but our calculator will. So that is really awesome with AP statistics, is that most of the math you really can do in your calculator. And I've heard some of my students who went on to make 5s, particularly I think the ones of mine who have made 5s, and I try to give this to future students, is that AP statistics is 2 things. Learning to interpret data, which I think is the hard part, and using your calculator. If you can do those 2 things, and you know what the different pieces of data mean, how to interpret a confidence interval, hypothesis test, and you know how to use your graphing calculator, you are good to go. All right, so quick poll here on which calculator you are familiar with. Do you have the TI-84, TI Inspire, Casio, or other? All right. So I'm going to give you guys a chance to answer. So hopefully me using my calculator is not going to be a complete waste. So far it doesn't look like it. I think we're all on the same page here. Cool, 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 cool. Wow. This is more than my class that I give them calculators to use. Sweet. All right, looks like we are at 100% TI-84. Okay. Which is awesome. So mine looks like this. Yours might be yellow. Most of my students are yellow because they're school property. And I can show you, we can walk through, you know, basically any problem we do using that. I do have computer software that we can do that with, so that's really cool. I've never taught an AP statistics class that was 100% TI-84, and those are the calculators I sign out to my students, so this is really surprising. I've always had 1 or 2 Inspires, a few Casios. One year I had a student who used Casio. It was my first year teaching stats, and I basically said, you're on your own, sorry. I don't know how to use that. But we got through it. And they passed the exam too, so that was good. So yeah, so you can do this in your calculator. Now, in the chat, since we're all on TI-84, yeah, TI-83 is the same thing. Inspire is the Gucci one. That's probably why I have the budget one. What function for this formula here would I use in my calculator? What would be the one that I would select if I wanted to calculate a confidence interval for proportions? So what is my calculator? It is not the vars stats button. That's a really good point. It is one prop z interval. So a little bit of calculator note here. Okay, I'll pull up my calculator. There are two menus that you want to be familiar with. Okay. All right, I need more calculator. I need more space. There we go. All right. So there are two menus you need to be familiar with. The first you need to be familiar with is the stat menu. Just press the stat button. Okay, so some options that you have there. You can enter data in. That's where stat edit comes into play. You can calculate things. So like if I want to calculate the mean from a data set, one variable stats. Standard deviation, because nobody likes that formula. Stat, calculate, one variable stats. And then under tests, we have a plethora of things that we use in AP Stats. And in this case, we are going to use a one prop z interval, or two prop if we were looking at two proportions, okay? All the way down to chi-squared, and then you got f-test. We don't use f-test. We sort of do linear regression. We do not do ANOVA for some reason. I wish. All right, guys, so technology decided to go nuts on us there. I don't know what happened, but we are back now, and we are going to finish up what we were talking about, which is confidence intervals for proportions, okay? So we talked about state, we talked about plan, we talked about do. So what we're going to look at doing now is concluding, okay, the last step. And that first line there is sort of your can statement that you need to know, learn it, know it, live it. Be sure that you are that you're up on that and you know what that is, okay? So we are however many percentage confident that the true proportion of whatever context we're talking about is between blank and blank. We are 95% confident that the true proportion of U.S. adults who like baseball is between blank and blank. Okay, so the three things that they're going to grade you on typically, if that's a free response question, you have to make sure you include the confidence level. If the problem asks for 95%, you mention 95%. Be sure to allude to the population proportion. And if you want to make sure that the reader knows you are trying to estimate the population proportion, not the sample proportion. If you use the words true proportion in your interpretation, that should be more than enough. And then also include context, okay? True proportion of all U.S. adults who like baseball, okay? Some sort of context about the problem. Don't just say true proportion is between blank and blank, all right? Those three things with the correct answer, you're good to go on the conclusion there. All right, so we're going to look at an example from the 2017 AP Statistics free response in which the manager of a local restaurant is concerned about customers who ask for a water cup when placing an order, but instead fill the cup with a soft drink. So in other words, stealing soft drinks. The manager selected a random sample of 80 customers who asked for a water cup when placing an order, and then found that 23 of those customers filled that cup with a soft drink from the beverage fountain. Okay, so part A is to construct and interpret a 95% confidence interval for the proportion of all customers who, having asked for a water cup, will fill it with a soft drink from the beverage fountain. Okay, that first sentence there, construct and interpret a 95% confidence interval, needs to be, that is your that is your cue to jump into that SPDC there, okay? You can go ahead and do that. So the first thing we need to do is we need to state, what is it that we are trying to estimate? We are trying to estimate the true proportion of customers who fill water cups with soft drinks. Okay, that is our big thing that we are trying to state, or we're trying to answer. Okay, so that's our state portion. We're stating what it is we're trying to estimate here. And we have a sample that we're going to use to broaden that horizon to a population. All right, we have to plan. We have our three conditions: random, independent, normal. For random, you're just quoting the problem, a random sample of 80 customers. Independent, I always take the sample size and multiply by 10 and say that that's reasonable for a population. It is reasonable to believe there are at least 800 customers at the restaurant who get water cups. Totally reasonable statement. And then normal, since it's proportions, we have to check our normal condition using the large counts condition. So 80 times 23 over 80, that's more than 10, it's 23. 23 successes, and then 80 times 57 over 80, 57 failures, okay, both greater than 10. All right, so for our do section, we have to, in our calculator, do a one prop z interval, and I'm going to show you all that real quick, okay? So I'm going to go to my stats menu, go over to tests. This is a one prop. We only have one proportion. We're not comparing two. So it is a one prop z interval, 23 successes, the ones who stole the soft drink, 80 in my sample, 95%. Paste. Notice I named my test since I used my calculator, and then I just wrote up the answer, okay, for my do section. I don't have to show my work on that formula there. Although that formula is important with multiple choice questions, being able to pick out which formula not worked out is the correct one based off of the three parts of the formula. So then our conclusion, we are 95% confident that the true proportion of customers who use a water cup for soft drinks is between 18% and 38% roughly. Okay, so a margin of error of about 10%. 28% is what we had from our calculator, from our sample, and then adding 10%, subtracting 10% roughly. All right. So part B, it says the manager estimates that each customer who asks for a water cup but fills it with a soft drink costs the restaurant about 25 cents. Suppose that in the month of June, 3,000 customers asked for a water cup when placing an order. Use the confidence interval constructed in A to give an interval estimate for the cost for the month of June. Okay? All this is some basic math. So take your confidence interval from part A, 18 to 38%, and then you're going to basically multiply that by 3,000 customers. That gives you the number, the raw number of customers who stole a soft drink, somewhere between those two numbers. And then for each customer, that's 25 cents. So also multiply those numbers by 25 cents. And you can see that the restaurant is losing somewhere between $141.24 and $290.01. So that is our confidence interval for the total cost to the restaurant from people stealing, our soft drinks. Okay, and then part C, the restaurant manager wants to be sure that his margin of error is 5% or less. So in that problem, based off of our one sample of 80, we had a margin of error of 10%, which is pretty high actually. So if that restaurant manager wanted to minimize that, we don't know what the sample proportion is anymore, but he wants to minimize that down to 5%. What should he do to be sure that his margin of error is 5%? We can make our sample size large enough to reduce our margin of error. Okay, so remember, the margin of error is the stuff after the plus minus sign. So the stuff that we are adding to our sample proportion and subtracting, and that number is equal. So that is consisted of our z-score, which for a 95% confidence interval, you can calculate using inverse normal based off of the tail probability. 95% in the middle, that leaves 2.5 on each tail. That's where the 2.5% came from. 0 and 1, since it's the z-score, it's a standard normal curve, which gives us 1.96. Okay, since we do not know the p-hat, we don't know for this new sample that we're making bigger what the proportion is. We're going to use 0.5. That gives us a standard error that is as high as it could possibly be. We want to overestimate because the highest our numerator can be is 0.5 times 0.5. Remember, that's p times 1 minus p. The highest combination you could ever have is 0.5 and 0.5. So we have all of our margin of error less than or equal to 0.05. This is where just basic algebra comes in. Divide both sides by 1.96, square both sides, move the n over to the other side, and then divide by that 0.0006577, which is 384.16. Our sample size needs to be larger than that, at least that, okay? Which we can't have 384.16 people, so we're going to round that up to 385. Always round up on your margin of error, okay, to be sure that you cover it. If you round down, you're going to be slightly higher than 5%, and we want to minimize that margin of error, okay? So yeah, kind of the trick there is to use 0.5 as your p-value since we don't know it, and then calculating your z-score based off of whatever confidence level the reader wants. All right, last thing, our non-negotiables. Number 1, be sure you know how to interpret the confidence level. So what does that 95% mean? It means that if I were to create several samples, okay, 95% of those samples would give me a confidence interval that would contain the true population proportion. So you're creating many samples, which results in many confidence intervals. Number 2, be able to construct and interpret a confidence interval. That's that whole SPDC process that we used, or phantom or panic, whichever one your teacher has taught you. Number 3, be able to identify confidence intervals and the margin of error on multiple choice questions. So they will give you a formula that is not worked out. So you need to be able to pick the right one based off the p-hat and based off the z-score, each individual part of all 3 parts. Be able to select your sample size to minimize your margin of error. That's what we just did. Understand the conditions for inference and be able to identify those and if any of those are missing, okay? So what are those conditions for inference? Random, independent, normal. And be able to identify if one of those are missing or if one of them is not met in a particular problem. So those are our non-negotiables. That's the big picture of what we just talked about today. If you have any other questions, hop over to the Discord statistics channel, and our awesome TA can help. I'll pop in there every now and then and also try to help. And also just building that community is fantastic. So it's what we're all about here at Fiveable. And we definitely want you to be a part of that as well. So, hope everybody has a great week. I apologize again for the technology issues and the splicing of video here on the replay, but we made it through, and I hope that everything goes better next time, and I will see you all in the next stream. Adios.